Scaling large reasoning models like DeepSeek R1 and Qwen 3 requires massive infrastructure. The computational inference costs required to run these models are soaring to unsustainable levels. Long chain of thought processing yields exceptionally high mathematical and logical accuracy. However, this verbose processing method has created a severe architectural bottleneck. This inefficiency is driven by the verbosity fallacy. The current models equate the sheer volume of text they produce with the rigor of their underlying logic. The root cause lies in current reinforcement learning paradigms. These training methodologies implicitly bind a model's logical correctness directly to the length of its reasoning trajectory. Because longer trajectories historically yielded higher reward scores, the system inadvertently trains models to extract rewards by outputting massive, exhausting token budgets for every single prompt. The bulk of this generated text is not spent executing critical logical steps. It is wasted on redundant linguistic filler, internal dialogue, and unnecessary conversational transitions. In the academic literature, this specific engineering failure state is documented as systemic overthinking. By rewarding verbosity, the AI industry has accidentally coupled advanced reasoning capabilities with extreme, unnecessary computational costs. To solve this, researchers developed the draft thinking paradigm. Up until now, the industry relied on post hoc truncation and length penalties to manage costs, but this fails. It blindly cuts off reasoning midway without altering the model's inherent tendency to babble. Draft thinking takes a different approach. It treats concise, efficient reasoning as a learnable, endogenous behavior rather than an external constraint applied after the fact. The architecture is forced to discard the noise and retain only the high-signal, key inferences that determine mathematical or logical correctness. True inference efficiency cannot be applied to a model as a band-aid. It must be internalized as a core cognitive pattern from the ground up. To build this endogenous capability, researchers utilize a strict three-stage progressive curriculum learning framework. This diagram outlines the training pipeline, beginning with Stage 1, draft structure acquisition via supervised fine-tuning. First, the system utilizes black box distillation to extract implicit, structured inference patterns from a massive 685 billion parameter teacher model, specifically DeepSeek v3. These advanced patterns are highly compressed and then injected directly into a much smaller student model. This compression is made possible by a mechanism called chunked symbolism. Look at this dense paragraph of conversational math reasoning. Derived from human cognitive science and working memory theory, chunked symbolism isolates the raw data. By aggressively abstracting the text, the process eliminates redundant natural language filler, forcing the model to rely exclusively on dense symbolic representations. Stage 1 successfully installs a reliable, low-budget reasoning framework. This creates the exact foundation required for the subsequent reinforcement learning stages. This optimization graph maps stages 2 and 3 of the curriculum, which rely on an incremental length expansion strategy during reinforcement learning. If the model is handed a massive token limit immediately during this phase, it will rapidly revert to its verbose chain of thought habits to extract higher rewards. The model's newly acquired low-budget preference must be stress-tested and stabilized sequentially to prevent behavioral relapse. In Stage 2, the model begins group relative policy optimization. The maximum generation length is clamped strictly at 3,000 tokens. During this constrained stage, the model trains exclusively on medium difficulty mathematical problems from the LIMO dataset. Moving to Stage 3, the token constraints are loosened to expand the model's problem-solving capacity up to 6,000 tokens. With this expanded limit, the training data shifts entirely to highly complex, elite competition math pulled from the AIM-24 dataset. This exposes the model to its absolute intellectual limits, while still enforcing a hard relative ceiling on verbosity. This incremental expansion ensures the model's reasoning depth scales perfectly with problem difficulty, cementing a permanent preference for efficiency. With training complete, we look at how this architecture operates during real-world deployment and inference. This flowchart illustrates adaptive prompting. This mechanic elevates reasoning depth from a fixed rule to a dynamically decidable dimension. Upon receiving a prompt, the model instantly performs an autonomous self-assessment of the problem's complexity. Simpler standard logic questions are routed down the fast, highly compressed draft mode lane. Highly complex tasks are routed toward exhaustive chain-of-thought processing. This routing occurs entirely within the model itself. Draft thinking eliminates the need for expensive, latency-heavy external routing modules. It delivers seamless, instantaneous adaptability. This bar chart displays the empirical validation of the draft thinking architecture against the baseline Qwen3 8B model on the rigorous Math 500 benchmark. The average reasoning budget plummets from 5,668 tokens down to 986. In economic terms, this represents an 82.6% reduction in computational inference cost. This massive token drop incurs a negligible 2.6% penalty in overall accuracy. To observe how these tokens were saved, we examine this stacked bar chart detailing the model's reasoning phases. The graph tracks a definitive behavioral shift in the model's problem-solving approach. Notice the systematic elimination of the redundant phase labeled Exploring Alternative Approaches. Without the wandering internal monologue, 100% of the model's compute is now laser-focused entirely on simplifying and computing expressions. Draft thinking proves definitively that the next frontier of optimal AI reasoning is defined by high-signal logic, not high-volume text.